Yeah, okay. I play tuba in a community band, and when we have a concert, the baseline for success is that the audience is larger than the band. So we're there. We are the last panel going, and we're going to talk a bit about the forest products industry, forest products in general, and it's what what we're doing with this resource, and how we can make better use of it in meeting some of the challenges we face in our today. So let me see what I've got here. My name is Ron Crotogino. I've been in the industry for quite a while. Actually started picking fir cones in 1959 for reforestation, and then went through university, working in a paper mill, and was able to actually come out debt-free, which can hardly be done now. Worked in research, worked in development of various sorts, and worked as an adjunct professor at McGill. Spent most of my time at Paprika, later became FP Innovations due to this guy here who sewed it all together, and then worked on nanocellulose, and this is where Richard's going to talk. So I've been involved with all of these people in some way or other. Where are we? That is hard to read. Can you make this display a touch larger? My glasses aren't that good.
Or you can take the mic and just stand here. Maybe.
Yeah, okay.
So the mic lifts out.
The mic lifts out. Okay, that's a good idea. Anyways, I better take this with me. Yeah, Canada has a tremendous amount of forests. Nearly 40% of Canada's area is covered by forests. Canada is has the third largest forest area in the world. I think Russia and Brazil are the other two countries that are bigger. And our forests constitute about 9% of the forests cover in the world. 90% of Canadian forests are government owned. This is very important. We'll find out later. They are sustainably managed in the sense that there have not been much of a change in forest cover over the last few years. The median age of a tree in Canadian forests is roughly 90 years now. And currently, Canadian forests emit more CO2 than they absorb, which is bad. Part of that is insect infestation, and of course wildfires, which are more recently in the news. The Canadian forests have been a tremendous generator of wealth over the years. We've produced from them products worth with a GDP about $35 billion. Currently harvesting about 0.2% of the forest area per year. So it's a fairly small percentage compared, for example, and the people who harvest the forest are obliged to replace them. Fire destroys about 6 times as much in a year. I'm not sure about, and insects a lot more than that. So when we talk about forest products industry and how much it impacts the trees, well, it's debatable. Forest products in the 20th century were used to created a lot of value in producing building products, paper products, the papers that you use, well, you used to read newspapers, hardly anybody does these days now. Sanitary products, which hasn't changed very much. In fact, it's the growth area. Packaging, where we lost our shirts to the plastics industry in the middle of the 20th century, and we're trying to gain that back. And of course, we make paper-making pulp for local use and for export. In the 21st century, which right about now, we're probably going to do the same sort of thing in terms of making the same products, but in addition, we will find that forest biomass is going to become an indispensable source of low-carbon feedstock for the manufacture of products deemed important for our way of life. The question is, this is to lower our carbon footprint. The challenge will be to make products at the right quality and price and create some attractive business opportunities. The panel objective is to ask the questions, how can we make best use of this resource? And to answer these questions, we have a very good panel of people from different backgrounds, but we all know each other and we've worked together at some point or other. We have Ian Delaroche, who has joined us today, just came over on the ferry. Ian is a plant geneticist. He worked for the first half of his career in that field and then joined the forest products industry and ultimately became a fierce advocate for getting more value out of wood products for the building sector. The second speaker we will have, we're going to speak in a different order than that's shown up here. The second speaker is Tom Browne, who is going to talk about, who has worked in the area of energy, mechanical pulping, and the biorefinery in his career at Paprika. And Tom is going to talk about a very interesting success story, making money out of lignin, which was said couldn't be done. And he did, with the help of a lot of very good people at Paprika. We have Richard. Tom became a member of the of CAE last year at Halifax. The next speaker got his little stamp of approval yesterday, and that's Richard Barry. Richard Barry is an exceptionally gifted chemist who, and who was more surprised than anybody else that we thought he was actually doing some tremendous engineering work. But he had a very strong focus on solving problems with his chemistry. So he worked on the fundamental end of it and on the practical end of it and made it all happen. He was very much involved in the environmental work, trying to reduce the detrimental effects of bleach plant effluents, saved the industry. He was part of a gang that saved the industry, I would say billions of dollars. And then more recently became involved in nanocellulose and took a process that produced grams per week and scaled it up into a plant that is producing tons per week. I would say that's process engineering in some ways. And then we have one more recent inductee, Bill Adams. Bill was inducted, I think, 3 or 4 years in 2021. He is an example of a guy that went out and worked in a whole bunch of different pulp mills in BC. He distinguished himself by showing that good application of sound engineering principles can save energy, can maximize production and quality and profitability and keep people employed. And he's now working for Mercer, expanding the reach of that company into more and more operations. And he's going to talk about he's a strategic planner in that sense. What do we got next? So that's our panel, and we will start the discussions by having Ian Delaroche tell us all about. He's going to tell us some tall stories about wooden structures, right?
Tall buildings.
Okay.
Well, thank you, Ron, for the introduction. And thank you all for holding out and being here. This is really great. Today I want to talk to you about wood construction and how it's helping decarbonize the building sector. You've taken that away.
Yeah.
Okay. All right. I'd like to just briefly highlight some of the key factors that are driving the global demand for housing. One of the key ones, of course, as you well can appreciate, is population growth. The world population is expected to increase by about 4 billion by the end of the 21st century. And these people will need shelter, will need housing. The UN has, in fact, projected a need for about 300 million housing units by 2030, and obviously that number will grow considerably. There's been another trend, and that is towards urbanization. 70% of the population will live in cities by 2050, and that will increase the demand for taller multifamily structures. So along with these increases, there's a growing demand for better quality, more affordable, and more environmentally sustainable housing. And I believe that wood will have a key role to play in this regard. Canada, as was mentioned by Ron, is endowed with a huge forest inventory, which will continue to grow. In fact, the recent federal initiative to plant 2 billion trees over the next 10 years is going to add to this significantly, and hopefully we'll be moving what is currently, with all these fires and disease, a source of emissions to an actual sink. Regarding sustainability, we continue to lead the world in a number of hectares of forests that are under third-party certification for sustainable forest management. And I won't say much more about this because Bill will be talking later and has a lot more to say on this subject and what this can mean to Canada's competitive position going forward. I might have just jumped too quickly. I should mention the point on carbon footprint and sustainability. I just want to emphasize that construction accounts for about 38% of the global CO2 emissions each year. The embodied energy of the building materials and the operating energy of the buildings are key contributors to these emissions. Now, operating energy is being addressed through regulation and incentives and has been reasonably successful. However, much more effort has to be directed towards reducing embodied energy. We can benchmark carbon intensity of construction materials using life cycle analysis. And when we, on the left, that figure that you see compares wood with other mainstream building materials. And it's pretty evident from that diagram that wood has a much softer carbon footprint, and therefore wood substitution will reduce carbon dioxide emissions. Another point on the right, as you can see, is that growing trees sequester carbon, which continues to be stored in the resulting forest products. This is sort of nature's version of carbon capture, use, and storage. So if we look at wood construction from the perspective of environmental benefits, 3 benefits jump out. First of all, it's a biomaterial, and by definition, renewable. Secondly, it has a lower carbon footprint as compared to all other building materials. And thirdly, it serves as a reservoir for capturing atmospheric carbon dioxide. I want to illustrate this with a practical example. 2 of them, actually. This is mass timber construction and tall buildings. The one on the left, actually in 2018, was the tallest building in the world. It's on the UBC campus, Browne Common. It's a dormitory, 18 stories. As you can see, quite an impressive structure. And that's made out of glulam and cross-laminated timber. The thing to note here is the huge amount of wood that's being used in this construction. You can see the numbers on the top. I've circled them. And you can go down and actually see how much carbon is sequestered. I think I have trouble seeing that, but I think it's about 1,700 or so. And then if you take the substitution, that is replacing wood as opposed to other materials, you add on almost 700 metric tons of carbon that are displaced. So all in all, if you look at it from a rule of thumb perspective of the numbers here, about 1 cubic meter of wood displaces about 1 metric ton of carbon dioxide, quite significant. Similar results, as you can see, are demonstrated on the other side. This is a 12-story condo in Quebec City, made out of mass timber. You look at the technology and innovation, and clearly engineering plays an enormously important role. You can see some of the performance enhancements that have occurred here. And as a result of this, I considered elegant work that has gone on, both from engineers working in academia as well as in commercial context, we can see that as a result, wood construction is safer, it's stronger, and the buildings are taller. Here are some examples of engineered wood products that are being used. And I particularly want to highlight the one on the top left, which is glulam, and down below and over, you can see CLT, or cross-laminated timber. These are the essential elements that have led to the successful renaissance of mass timber high-rise construction. Another important aspect is that wood is now used effectively in combination with other mainstream materials, and that it would be steel and concrete. And there you're seeing examples of hybrid systems, roof, flooring, and what have you, with the combination of these various materials. UBC has been a hotbed for research and innovation in building systems, particularly when it comes to mass timber and hybrid construction. If you look on the top left, you can see again the building of Browne Common. 17 stories, 17 floors were actually put together in 9 weeks using, again, CLT and glulam. That's 2 stories per week actually being installed, which is pretty phenomenal when you compare it to concrete construction. So the sweet spot mid-rise, which is between 7 and 12 stories, and hybrid construction. In other words, putting wood together or mass timber together with other mainstream products. In the last 5 years, there's been over 700 residential, commercial, and institutional mid-rise hybrid structures that have been built in North America. These structures are cost competitive with steel and concrete alternatives. And you'll see on the left a good example. That's a 7-story mid-rise condominium in Seattle. 5 stories are wood frame, platform wood frame, which you normally use to build houses in North America for 5 stories, and it's on a 2-story concrete podium. On the right-hand side, we show the T3 mass timber mid-rise. This is 9 stories, and this prototype has been replicated across North American cities. Been very successful, well received, particularly by the high-tech, knowledge-intensive sector. And you can see why when you look at those pictures. They offer really a new office experience, which is built around environmental sustainability, obviously, biophilia, which is the love of nature, tying it in with nature, the aesthetics of wood as compared to other materials, and of course, the level of functionality that we now get thanks to the engineering developments. Well, what's the impact of wood construction as it affects Canadians? And I put a list here of 6 points that I think are quite relevant in this regard. The first is that wood construction is helping Canadians meet the growing demand for housing, and particularly as we move towards a net zero energy situation. And this is particularly important for remote and First Nation communities. The other point is it's helping diversify the forest sector. Another point is the revitalization of Canadian forest-based communities across Canada. And in fact, coincidentally, Tom and I worked on a project, a city in Quesnel, that was really looking at ways to revitalize that community and tie it in with First Nations and what have you. And I think our study set the course for, I think, quite an interesting approach going forward for that particular location. Another point is, and a very important point in my mind, it provides new revenue for forest management initiatives. And this can directly help mitigate, I mean, again, the point being the sink versus the source situation with these fires. We don't have the same situation, and it's very forested in Germany, it's very forested in Sweden and other places, and they manage. We do extensive forest management, in fact, very little management of our forests, if you look at the boreal, across the boreal, and as a result, we're having these problems. Whereas in areas where it's a little more intensive, multi-use, hunting and what have you, and all the uses that people have in Europe for their forest, they're more sustainable in terms of resisting biotic and abiotic stresses. And the last, and I think the most important thing, is it's helping grow the Canadian GDP while meeting our greenhouse gas emission targets. There's a growing movement to ban all logging by activist groups in Canada and, in fact, around the world. And we, I think, as professionals, have to do a much better job of presenting the alternative position. And some of the things that I've listed here tie around quantification of the economic, social, environmental impacts of non-intervention, and I just spoke to that a minute ago. And the idea here is to help mitigate biotic and abiotic stresses that are affecting our forests, which are being exacerbated by climate change, as we all know. The other point that I have is the suggestion that we can use LCA, life cycle analysis, more effectively, and covering the full value chain from the actual seed to the built environment to the recycling of these materials. In other words, fully exploiting the natural advantages we have in terms of a circular bioeconomy. And my next point is the documentation of chain of custody throughout that value chain. This is an advantage that we can well have, tied back to what I mentioned earlier about the certification we have in our forests, carrying it all the way through to the product and its use in the built environment. And the last point I'm making is to take full advantage of third-party certification. And those are the key issues, I think, that can help prosecute a more effective case and is not, as was mentioned earlier, a situation of greenwashing. My last slide, 3 messages I would leave you with. One is what we're seeing is an explosion of new technologies and innovations with engineering at the forefront. The second point I would make is wood products is playing and will continue to play a very key role in decarbonizing the construction sector, which accounts for 38% of the total emissions globally. And my last point is that with the growing threat to harvesting by activists, there is a need to be countering that with solid data and not greenwashing. So on that note, I will end, and I guess you want to come back up and introduce the next person.
Our next speaker will be Tom Browne, and he's going to talk about the biorefinery and a very interesting example that ties in with Ian's talk. The thing that holds all those pieces of wood together are glue, and the material that he's going to talk about was the glue that held the fibers together in the first place and how to reprocess it.
All right, well, thank you, Ron, and thanks to all of you for sticking around. I know it's hard being last. So I've been asked to talk about the, first of all, the concept of the forest biorefinery, and secondly, one of the materials that come out of that, which is lignin. And I've been using this slide for a number of years. The model of a generic refinery is that it takes in some raw material and converts it into a variety of products. First of all, often a commodity of some kind, like a fuel, large volume, low margins, but also with some specialty grades that might be small volumes but high value. And you go around that box generating value until what's left is very hard to do anything useful with, and so that gets used to run your mill usually, and possibly to sell some power into the grid. The forest biorefinery today, to back up a little bit from Ian's presentation, starts with whole logs, and mostly they go to the sawmill. We don't cut whole logs to make paper. They go to the sawmill, and they become lumber and a variety of engineered wood products like the CLT, the glue lam, plywoods, things like that. What comes out of the sawmill as residues, there's 2 kinds of residues. First, there's the bark and sawdust, and that's the red line. But we also get wood chips out of the sawmill, because if you think about a tree, which is round, and 2x4s that are rectangular, you're going to have long, skinny leftover bits, and that gets put through the chipper and goes to the pulp and paper mill. The pulp mill also generates a residual stream that gets burned, and I'm going to talk about that a little more later on. And that all gets burned for heat and power within the pulp mill, allowing the pulp mill to be essentially off-grid if you do it right. A little bit of fossil fuel needed, and it's possible to generate as much power as you use on site, and maybe even make a bit more for export if you've got enough bark. So that's the forest biorefinery as it stands today. And I think what I want to introduce is the concept of the new forest biorefinery, where we identify other things to do with some of those wood chips, given the changes in the demand for pulp and paper. And I think Richard's going to talk a little bit about some of those pathways, but also to make better use of the residues. You'll notice that the red line from that chemicals and materials box has arrows at both ends. So you can take some of those residue streams and see if you can do better things with them. And so that's the part I want to talk about a little more. But before I talk about the residue streams, I want to point out one important difference between the forest biorefinery and a petrochemical refinery, and that is that wood, unlike oil, is scattered thinly all over the landscape, and it costs a lot of money to go out and collect it. And the implication of that is that economies of scale lead to a point where your marginal tons of wood get very expensive because you have to go a long way to get them, and it's just a lot of trucking. And so I've got a couple of examples here of refinery scales where I've used, as an indicator of scale, the energy content per unit of time entering the mill in the feedstock. So there was a Shell oil refinery shut a long time ago in Montreal that consumed 130,000 barrels a day, and I think I've done the math right. That works out to 9 gigawatts thermal entering the mill. A couple of other numbers there. Canada's largest pulp mill consumes something of the order of 5,000 oven-dry tons of wood per day. I'll point out that that's an awful lot of trucks entering the gate. I don't know if anyone wants to hazard a guess. That's 1 gigawatt. So we're quite a lot smaller than even an obsolete small refinery in East End Montreal. I gather the largest petroleum refinery today is in India and is 1.2 million barrels a day, so 10 times the size of that obsolete Shell oil refinery. And even the biggest mills in the world, which are in Brazil, where the trees grow a lot faster and you don't have to go as far, they're only 3 or 4 gigawatts in terms of thermal content. And part of it is the distance, but another part of it is you can imagine the number of trucks per day that we're talking about to get the wood in the door. So we're always going to suffer from economies of scale compared to a petrochemical refinery. We can't compete on an even on an even basis there. So moving on to lignin. Trees are Mother Nature's fiber-reinforced composite, and lignin is the glue for the cellulose fibers. Lignin is also Mother Nature's aromatic molecule. It has a benzene ring in it, in the polymer, and this is the only large-scale natural aromatic molecule available to us. It's removed in most pulping operations and burned. It's burned for heat and power, but it's also burned to drive. There is a particular chemical reaction within the mill that's absolutely critical and which is endothermic, so it needs heat to proceed. So it's not just steam and power for the grid, but it's also to drive internal chemical reactions that are absolutely critical. But the good news is there's more lignin than we need for that purpose available in the tree. I've been told, I'm a mechanical engineer by training, I've been told by the chemists that if I'm going to talk about lignin, I should show the molecule. So there it is. And moving right along to new products that you can make. There are new products you can make, and these are being done today. You can make phenolic resins, phenolformaldehyde resins, for plywood from lignin, and that's being done. And that's an example of something you can do within the forest sector. And in fact, that was the first product we developed because we developed the lignin process to extract lignin from the pulp mill, but it was pretty clear we needed to have a launch market. And so at the same time, we developed the glue for plywood, and that's our cousins down the highway, so it's relatively straightforward. Outside the forest industry, polyurethane foams is an example of a place where you can replace the polyol component with lignin. And there are a number of other aromatic pathways, but I think this is the opportunity. There's an opportunity here, and I'm going to quantify that opportunity. But first I want to point out that this isn't rocket science. It was done in the 50s and 60s. The Arborite Company used lignin from the pulp mill in Cornwall, Ontario, and used it to laminate together their kitchen countertops in the 1950s and 60s. The next slide shows why they stopped. This is plywood resin prices, and that's dollars per ton as a function of oil prices in dollars per barrel, corrected for inflation. Now the upper left little red box makes the point that the prices for 1955 and 1960 were in the $3,000 to $4,000 a ton. They're off the top of that chart, and that's because this was a war material. It was very high tech, but the chemists hadn't quite figured out all the steps, and so there were a lot of inefficiencies. By 1965, they'd figured out how to make it a lot cheaper. I've also left 1980 out of the regression there simply because oil prices spiked in 1980, but the resin manufacturers didn't respond by upping their prices. So if you look at the other prices, that's a nice straight line. And I know it's is it causality or is it just correlation? But you can look at this and infer that even if oil were free, it would still cost close to $600 to make a ton of the resin. And this is part of my point about not being able to compete with oil. We can't compete with ethylene, for instance, because the price of making ethylene is the price of the barrel plus one transformation step. But these phenolic resins are multiple transformation steps beyond the barrel, and now we have an opportunity to compete. And it turns out, anecdotally, from people who are doing this, who don't want to share details but who have let slip here and there, the break-even point is around $50 a barrel. Above $50 a barrel, we're cheaper. So we can compete without any carbon taxes, without any kind of support. We can compete against oil in phenol formaldehyde resins as long as the price of oil is above, $50, $60, something like that. So talking about value versus volume, lignin, I've put cellulose fibers in the middle of that chart just to give you a feel for what the market looks like. A couple 100 million tons a year of cellulose fibers are sold at prices in the $1,000 or maybe a bit less per ton range. If we tried to make fuels out of lignin, the market is enormous, but we can't afford it. It's way too cheap. We just cannot do it. You need an awful lot of carbon taxes to make that make that work. The sweet spot is markets where you've got million or 10 million ton a year markets and prices in the $1,000 to $3,000 a ton range. That's where we can compete against oil. Now you'll get a lot of people talking about the specialty grades. You'll go to conferences and hear about carbon fiber from lignin, and that's a nice pathway, but that's only going to be 1 or 2 mills that are going to be able to do that before they've saturated the market. They'll get good prices, but it's not a solution for everybody. And PF resins and polyurethane foams are in that sweet spot, as it turns out. So, world lignin capacity today, or kraft lignin specifically, which comes from kraft pulp mills, is 150,000 tons. And there are about 5 or 6 plants listed there. I'm going to point to the West Fraser mill in Hinton, Alberta. That's the technology that my team developed. It's only 10,000 tons a year. That's the only Canadian plant doing this at the moment. And West Fraser, was an early adopter, but it helped that the company also had plywood assets. So they had an internal market. So once the board and the CEO had decided to go this route, the plywood mill, I remember the plywood mill manager was told he was going to do this whether he liked it or not. And when he discovered how much money he was saving, all of a sudden he loved it. But having the CEO telling him this was a lot more effective than a bunch of researchers going in and telling him he was going to save money. Now there's another piece to this. and that is that on Thursday last week, I found out that the Stora Enso mill in Finland is about to be shut. And that means that lignin is going to disappear. That 50,000 tons a year is going to disappear. The reason for the shuttering is that this is a mill in eastern Finland and has relied historically for wood from Russia. And they've not been able to source wood that's cheap enough to make up for the loss of that wood supply. But that's going to affect the world lignin capacity. It's no longer 150,000 tons, it'll be 100,000 tons. That's a third of world capacity gone overnight. And it does make the point that you lose the pulp mill, you lose the lignin plant because they're co-products. Right? So the potential for new kraft lignin plants, phenylformaldehyde resins and polyurethane foams are both million-ton-a-year markets. And anecdotally, as I said, the break-even point is in the $50 to $60 barrel range. Worldwide, the potential for lignin production is about 8 million tons. Current is 150, and by fall it'll be 100,000 tons when that mill shuts. In Canada, the potential is 1 million tons a year if every mill in the country chose to extract lignin. The current capacity is 10,000 tons, and anecdotally, all those plants are sold out. And incidentally, Stora Enso has made the point that they're going to build another lignin plant. They see it as a valuable asset, but they're going to build it in Sweden where it doesn't depend on Russian wood. So yeah, the old joke is you can make anything with lignin, except money. So I think that's true if oil is $20. But I don't think oil is ever going to be $20 in any volume anytime soon. So I think we can agree that you can make money with lignin. I'm working on an Ontario case study at the moment. Potentially, Northern Ontario, there's about 100,000 tons of lignin available without affecting mill operations. The necessary heat can be found with bark and sawdust and energy efficiency. You would use it in plywood and panel mills in the north, but also Sarnia and manufacturing in the south. And this mirrors the EU approach to the Port of Rotterdam. Very simple. So there's lots of opportunities. My last slide, what are the challenges? Well, there's technical challenges. There's been 100 years of R&D into petrochemicals and only 20 or 30 into lignin. There's purity, you have to depolymerize this huge molecule. There's the consistency from batch to batch. There's color and odor issues in some instances. Standard testing methods need to be developed, and we're working with the Canadian Standards Association to do that. But the biggest challenge, in my view, has been market pull. We did all this with push, and it was only after West Fraser started buying less resins that all of a sudden their resin supplier was saying, "Why are you buying less resin?" "Oh, because we're using this wonderful new product." And now they wanted to know about it and start understanding how they could, because up until then they didn't care. So links to other industries, that's why I'm here. And obviously it'd be nicer if there were more people here, but hopefully the message will get out. And so thank you for your attention, and I'll stop there.
Richard, you're on deck. Richard is going to talk about nanocellulose.
Well, good afternoon. Thank you for being here. Appreciate it. We've heard a lot about electrons and photons and neutrons. I'm going to talk about what chemists love, which is molecules. And so talking about matter, mass, rather than energy. And in particular, I'm going to be talking about the main material that is critical in the forest sector, and that's, from my point of view, cellulose. And cellulose is still very much something that, as a market, is still thriving. But what we have recognized recently is there's new forms of cellulose that are opening up new opportunities for the material. And what I'm going to do in the next few minutes is introduce those new forms with emphasis on nanomaterials and particularly cellulose nanocrystals. And why these are intriguing is because it's more quantum effects rather than classical effects that begin to occur when you start using these kind of materials. So when we started this work, there was a lot of promise, but as many will have recognized, promise to practice generally takes a lot of patience to bring it to fruition. So what we're involved in is cellulose deconstruction. So what we presently are using in the industry to a big degree is wood fibers. But within that structure, there are macrofibrils. Those macrofibrils are made of microfibrils, and within that, there's nanofibrils. And what we've begun to realize is if we start breaking down this structure, and we can do that mechanically by using refining processes. And Dick Karekis is here, a world expert on refining, and he will be able to tell us a lot more about how you achieve that goal. But when you start doing that, it changes the property of the cellulose. Beyond that, you can also do something chemically with it. So you can use concentrated hydrolysis media. In our case, we use sulfuric acid. And what you can then do is break down the amorphous element that's in the fiber and liberate the crystalline component. And those crystals are what really provides the tremendous strength that we have in trees, in paper, in all of the products that are made from cellulose. And the image you see here is an atomic force microscope image. And these particles are somewhere around 5 nanometers in diameter and about 100 nanometers in length. And they also, by the process that we use, there's a charge placed on the surface. And this creates a particle that's got an aspect ratio and also can be suspended stably as in colloidal suspension. So what we have now been able to begin to develop is a new cellulosic industry. And depending on how much work you put into the process, as you might expect, the amount of tonnage that's produced of these materials decreases from that that's easy to that that's more challenging. So the microfibrillaceous cellulose component is about 22,000 tons per year of that that's being produced. And that's typically being produced by the traditional manufacturers of cellulosic materials, so the conventional pulp and paper industry. Cellulose filaments is a particular Canadian version of this, and it sort of falls between microfibrillar and nanofibrillar cellulose. And in this case, Kruger Bioproducts is one of the practitioners of this, and also Performance Biofilaments. I think, Bill, you're part of that process with Mercer, and Resolute is the other partner in that. Then we go to another scale, cellulose nanofibrils, where there's still a larger aspect ratio. These provide incredible strengthening properties to traditional products and also have their own non-traditional product opportunities. And the greatest group that's working on this is probably the Japanese industry. And the area that's most close to my heart is cellulose nanocrystals. And CelluForce is where I spent the last 10 years working on the process, some of the regulatory elements associated with it, and also the markets. And there's not a lot of this material produced. It's about 700 tons per year, but 300 tons of that is produced by CelluForce. So we are the leaders, we were the first, and we're still in that position. I was glad to hear that Heather said a mine takes, I think, 17 years to be able to be brought to fruition. What we find with any kind of material, it takes time to go through the process. The actual element that is the crystal was first discovered in the 40s, but it took a long time for it to be anything else but a curiosity. In the 90s, McGill University looked at the properties of this material. Derek Gray, in particular, was looking at the liquid crystal properties of this material in suspensions. And when you dry this down, you can produce beautiful films that have structural color associated with it. But because of the small size, it's affected by magnetic fields, for example, that allow for these kind of effects to be obtained. Anyway, as I think Ron mentioned, what they were working with was gram quantities of this material. So we worked out how to be able to scale this up in a pilot facility. And we did a good enough job of that we actually got the financing to be able to build a plant. And this plant was put in Windsor, Quebec, next to the Domtar mill. A few years after that, we were able to actually generate the first application of this at commercial level, and that was with Schlumberger in the oil and gas industry. So the manufacturing process is actually, when you look at any manufacturing process, put it in a block diagram, looks very simple. The grinding and the reaction are. The part that's difficult is the separation and concentration. So in that situation, you've got to take out the sugars and the acid that you've generated and you've been using from the crystals, and you then have to make use of the sugars in some way. You've got to destroy those, use it as an energy source, and also recover the acid, so make a closed-loop process. And that was all achieved. And so we have a production facility, as I mentioned, in Windsor, Quebec, a capacity of 300 tons. It can produce it as a spray-dried powder and as also a never-dried suspension. And both of those are actually used by commercial partners. The news is good enough that we're now looking on expansion to 600 tons per year. There's certification of the plant, and also because it's actually used in some cosmetic formulations, it has an excipient grade product certification. So what are the attributes of this material? What it does is, because of the small scale, it forms very dense coatings. And so it can form a barrier layer that prevents the passage of oxygen and carbon dioxide, for example, on packages. It viscosifies. It basically can displace polymer viscosifiers. Therefore, it means that you have a sustainable non-petroleum basis for viscosification. And I'll talk about an example as a commercial product in a moment. The material, and I think Tom was mentioning this is the strength element. We have a composite structure in trees, and the lignin is the glue. Well, the cellulose, and particularly the nanocrystals, are the strengthening agent that is like the strengthening fiber in a resin structure. I mentioned liquid crystal performance. So what happens is that the material forms a scaffold, a liquid scaffold within suspensions. And what this allows is for better suspension of pigments. Propants in the oil and gas industry or pigments in the paint industry, these can be better suspended because of this material. And because you can do this at 300 degrees centigrade, you can still be able to get good suspension at very high temperatures. The surface of the crystals have hydrophobic and hydrophilic facets, and because of this, it acts as a surfactant. So you produce Pickering emulsions with this kind of material. So it can be used in oil-water structures, and you can change the structure of the micelles by the amount of the material placed in there, or use other surfactants associated. And this has been the basis of bio paint that is now on the marketplace. It can also act as a lubricant. So in water-based lubrication, particularly in drilling systems, you can add CNC into those systems, and it will improve the durability because of the lubrication that you're using. The other thing about this is it's got a surface that's hydroxyl rich, so you have a reactive environment where you can add other types of material to it. It's a sustainable material. It's produced from a bleached chemical pulp. It's 100% bio-based. And one of the advantages is it's marine biodegradable, and there's one particular application where that is particularly important. Also, because it's produced in Quebec, the Domtar mill, the energy sources are sustainable. So what are the markets and commercial applications? The ones in red here are where we actually presently have a commercial application. So oil and gas is one, largely because of the suspending and barrier properties that are generated. Paints, inks, and coatings. Paints and inks because you can suspend pigments better. Coatings because of the barrier properties. You can place this onto plastics and actually avoid the use of PVDC, and therefore you can make the plastic something that can be actually recycled. Rubbers and elastomers, there's now on the marketplace biodegradable rubber gloves that are created by the use of the cellulose within it. And a big one now is actually cosmetics. So what I'm trying to suggest to you is that there is a 21st century cellulose industry that is beginning to be developed. We have commercial applications with several major players in non-traditional sectors. Gas barrier properties are one of the big ones for the brand names. They're looking for sustainable packaging options. Non-contaminating sealing of drilled porous strata, that's where the oil and gas industry is most interested. Biodegradable rubber gloves. There's such a production of rubber gloves that we've had during the pandemic that this is allowing for those things to probably, if this happens again, which it probably will at one point, that we will have a better way of disposing of those gloves. But the one big one that's presently coming through is biodegradable sunscreen. So the fact that it's marine biodegradable means that you can basically take this as a carrier for sunscreen active ingredients, and you get better biodegradability of the whole structure. And this is important, in fact, for coral reefs because they've been finding that the sunscreen active ingredients are one of the elements that causes destruction of coral reefs. One of the elements I talked about is viscosification, and during the pandemic, locally, we couldn't get hold of the polymers that were needed for hand sanitizers. And so by using the cellulose nanocrystals, we were actually able to use it as a viscosifier in that application. That didn't continue. The polymer supply came back again, but there were enough companies that started to use it that they began to recognize there was an opportunity here. And for me, this is just the beginning, because there is about 100 patents per month on cellulose nanocrystals. There are over 500 publications per month on cellulose nanocrystals. And just this last week, there's actually been a nanotechnology conference that's basically associated with crystals, fibrils. And this is where the new engineers, the new scientists are actually spending their time. So there's a new generation of cellulose scientists and engineers that we are exposing to the industry and what is possible. And the reason why all of this was done in the first place was because there was a decline in the forest sector that probably was most evident during the early 2000s, and it had to be reversed. And there were several initiatives that were put in place, and Ian was a big part of the development of that. And those things have worked. And you'll see from this particular slide, apart from the COVID dip that there was 2021, that these new products and also structural lumber has changed the direction. And so we are back again producing monies for export products. Thank you very much.
Our last speaker is Bill Adams. And come on up.
Yeah, hello everyone. It's great to be here. I don't know if I've ever been the very last speaker in the last session of a conference, but still great to be here, and hopefully you'll have an opportunity to maybe get a new insight into the important role that forest products play in mitigating climate change. And I don't think I would be too bold to say that, without actually getting this right in Canada, we literally have no choice of kind of meeting our climate ambitions. So yeah, this is, to me, very passionate about helping people understand this, because I think it is one of the things we we have a great deal of stakeholders that don't really fully understand the benefits. And it's nice to see the speakers before me. I think there's going to be kind of a lot of tie-in here in terms of some of the things I'll be presenting. So maybe just to start and kind of give you a little bit of context of where, the role that I have. So I work, I'm the VP of Sustainability and Innovation at Mercer International. So we're a global forest products company, but based in Vancouver. We have about half our operations in Germany. Kind of an interesting theme here this afternoon about, and I will get into that a little bit today. We have, 5 pulp mills. We produce about 2 terawatt hours of power, and about a quarter of that is actually sold as renewable energy to the grid, both in our Canadian and German mills. We're the largest mass timber producer in North America now. We bought the largest plant in Spokane, Washington, a couple of years ago, a year and a half ago. We just recently bought Structurlam, which is based out of BC. They have a large operation in Conway, Arkansas. So we have about 50% of the North America's capacity in cross-laminated timber and glulam beams. So really growth segment for us, and partly because of the ability of this mass timber to provide such large carbon benefits to society and building materials. So that's kind of our footprint, somewhat integrated. We've got really 2 top-notch sawmills in Germany. One of them is the largest European pallet manufacturer, so shipping pallets from dimensional lower-grade lumber. We make briquettes and pellets there as well, but kind of a unique company in that respect. So really, this is sort of the one question of the day in my presentation. If you were to look at where this might be in the world, approximately 11 million hectares of forest, 78 million cubic meters of harvesting, a very large benefit to the carbon equation in that particular region. And in general, the forests are growing at about 1% per year. So and we've touched on this, throughout the conference, I'm sure, regarding the economic benefits, especially to rural communities in what the bioeconomy can bring. So in this case, unfortunately, it wasn't Canada, it was actually Germany. And so to see a country with such a small forest footprint, to see them take the full advantage of that and how much of a climate solution it is, and even the recognition in their stakeholders, how important that is both for the economy and for climate change, something we still have failed to do so far in BC. So here's BC. We have 5 times the forests. We harvest about 2/3 the amount, and this is likely to drop with continued policy decisions in BC. Probably will go to maybe 35 or 40 million cubic meters in British Columbia. Our forests are a mass net emitter, not just related to forest fires, but insect infestations and just forests that are way beyond their natural maturity. But we've done such a good job fighting forest fires since the late 40s that we've completely distorted the age class and made them way more susceptible to forest fires and less resilient to climate change. And then, just even looking at slash burning in British Columbia, where, it's something that when you tell the German that's what you're doing with the waste material, they kind of look at you funny, like, why would you want to waste 5, and actually end up being a large net emitter? And right now, our industry in BC is really struggling. We have, it's the highest cost jurisdiction now for wood in the world. We're first to take downtime when prices get low, and the bioeconomy is really suffering for long-term economical supply, and it's pretty much the foundation of any investment decision that you make. So, but many of these are deliberate policy choices. So just look at how a German understands the role of forestry. You've got the role of the forest storage in 58 million tons of storage. The storage in just even in the manufacturing sector in Germany in terms of harvested wood products, providing solutions in that sector. We talked, a lot about the substitution effect when you use products for society that are lower carbon intensity than which wood is compared to single-use plastics and concrete and steel. There's obviously a major carbon benefit, and so it just kind of shows you what is possible. And if you looked at just British Columbia, and if we took kind of a similar approach, and recognizing we have a whole different dimension, we have old-growth forests, which have particular important biodiversity conservation benefits as well. They're not forests that go through natural cycles of burning or insect infestation every 80, 90 years. They're actually forests that last 250, 300 years and have a very stable carbon. So we're really talking about things like boreal forests or montane forests in the Prince George region. If we manage those in a sustainable way, we could literally quadruple the size and the economic benefits of the industry here in British Columbia. So this is probably my favorite slide, and it's a great slide to really help people understand how you need to look at the role that forest products plays in mitigating climate change. And we talked, people explained it in different ways, but I've always taken kind of the 3-bucket way. And, the first bucket is in the forest. So we need to be able to, as operators of the forest, be able to show that the forest that's growing each year and the forest that we're harvesting each year, that we're actually doing it in a sustainable way. That's kind of the foundation. Ian talked about certification. That's like the basis of certification. Obviously, there's a lot of other things around biodiversity and indigenous rights and other requirements that are related to forest certification. But the primary one is, are you harvesting in a sustainable way? What's the annual yield? And how much are you harvesting? And is that actually growing in carbon? So that's kind of, we call that bucket number 1. Bucket number 2, and this is actually a great, a lot of the NGOs remind us that, it takes carbon emissions to run your mills, to get your wood to your sawmills, your residuals to your pulp mills, and other, bioproducts end uses. It takes carbon emissions to get your products to market. And I think it's a very legitimate claim to make, that we need to make sure we consider this. And we call that bucket number 2. It takes carbon emissions. One of the, our responsibilities, to be honest, part of our social license to operate is to figure out how to get to, a net zero pulp mill. And, today it's actually possible. Probably the last 4 or 5 mills that are built around the world, Äänekoski in Finland by Metsä, some of the South American mills, the new Kemi mill, all, maybe 10, 20 kilograms of CO2 emissions per ton of pulp, compared to, say, what would be in BC, would an average would be more like 300. So we've got a lot of work to do. The technologies are there. The economics is still a bit challenging. We've got some work to do, but bucket 2 is an important parameter to recognize. But I think one of the biggest buckets that we don't have a very good understanding in terms of our stakeholders and society in general is that important role that forest products play in the substitution of more carbon-intensive products that are providing solutions to society. And I think when we really look at that, it's actually often many times the benefit of even just, if you're managing your forest right, you should be increasing the level of carbon in the forest. Obviously, we're going to be a negative impact on bucket 2, but bucket 3 can actually be very substantial. And what we're seeing now is that companies are starting to look at that this way and doing the calculation. So we actually had a project in northern Alberta. We have a mill that operates there in Peace River. It's a combination of hardwood and softwood pulp. Also produces a lot of energy as well. We actually got together with all the other companies that harvest in that general area. It's quite a large area. It's about 7 million hectares. So if you think about it, it's about the size of Austria. And we looked at all that forest, how much was being harvested, what kinds of products were being made, how much emissions do we take to produce all of that? So that would be the bucket 2. And then bucket 3, which is what are those products, and how do those products play in terms of substituting other products in the marketplace. So you can kind of see where we're at. So that was about 7.3 million hectares. For those who are, just quickly, there's the kind of the map of the area that we selected. And this is the 2020 year that we took all of the data, all the harvesting data. We used the Canadian Forest Services model, which is an incredible spatial model which allows a forest company to look at all the forest, the age classification, and then look at the yields and look at how much new carbon is growing. This is probably one of the most interesting facts that came out of it for me and really helping understand that. So if you look at, in Alberta, the boreal forest there, some of them last 55 to 70 years. In our East FMA, it's a little bit higher, maybe 70 to 90 years, or 75 to 90 years, sort of natural. So over the last 10,000 years, those forests get destroyed by fire or insects or whatever, and they regenerate, and they've been doing that for forever. But what you see here actually is a much older forest than is traditional. And again, this is back to very successful forest fire fighting, but on forests that are actually normally go through these natural disturbances. And it's really we're really starting to see that effect right across Canada, where our forests are actually way too old. It actually is compromising biodiversity. It doesn't have sort of the natural age classification that would be traditional. But this was very insightful because it also is helping us understand that actually sustainably managed working forests are far more fire resilient than we have today in Canada. And that is a very big problem. And when you look at Germany, when you look at Sweden, when you look at Finland, they just don't have that issue because their forests are much more intensively managed. And the sort of this conservation of forests that go through these cycles is not something that the science that they would utilize to make forest policy. So in particular, in this year, you can see the how you would do a modeling. You've got gross growth about 4 tons of carbon per hectare per year. So that's basically the kind of the growth rate of the forest in this particular sector. So this is kind of what the modeling allows you to generate. You got to take away your annual litter fall and your annual mortality, the natural mortality that happens. You can see on the contributing land base, you've got harvesting. So this is the drawdown. Obviously, when you harvest, you're removing that carbon from the forest. You've got to be able to subtract that. So basically, the forests, there's about 3.5 million hectares of contributing forest. If you multiply that by 0.39, and then there's about 2 million 2 million hectares of treed forest, and it's about the same. And that actually generates about 2.3 additional tons of carbon being sequestered in that particular 7 million hectare region. It's kind of a busy slide, but really just, again, a response in how companies are dealing with this bucket 2. So we've actually, our particular company, and actually if you looked at Canfor and West Fraser, Resolute, Domtar, they're all signatories to the Science-Based Target Initiative, and that requires us to use a very strict methodology to look at all of Scope 3's emissions. So there's many categories, things like Category 1, which is around how intensive is your forestry in terms of carbon intensive and all the chemicals you purchase. So you actually do all the calculations, you work through your supply chain, you work with all your suppliers, and you gather all this information, and it allows you to report. So if I was to go back to all of the contributors to our project in Northern Alberta, it was roughly about 600,000 tons of carbon emitted as a result of fossil fuels being used in all of their supply chain. So it really gives you an indication. It's actually quite significant and work that we have to reduce. And here's my last slide, really great backup slide for Tom. You know, in the year 2022, Mercer had a record year. Financially, one of the reasons we did is we sold electricity in Germany, so all of the electricity exports that we had, you know, we were averaging, you know, well over 200 euros per megawatt hour for the entire year. One of our mills exports, you know, 60 megs every hour. So, yeah, so here we are at the same time, which we're using lignin to produce electricity and selling it for record prices. And our entire ambition is to get out of the electricity business, make just enough electricity to run our plant, and take that lignin and make products, biomaterial products. We feel that the long-term opportunity and the climate benefits of biomaterials, especially if we can get those biomaterials as part of the circular economy. So we've actually built our plant in Central, it's at one of our pulp mills, our Rosenthal mill. It's a 1 ton a day plant, which will give us a really good opportunity to work with all of these partners. But again, it shows you the kinds of thinking that forest products are getting into. So that's my last slide, and I guess we'll open it up for discussion and questions.
Nice to hear about the lignin plant.
Thank you, Ian, Tom, Richard, and Bill, for very interesting presentations. I'm going to open the floor for questions.
Well, I think the obvious one was, so if our forest management processes seem to be inferior to German management processes, why don't we change them?
I think that one's for you, Bill.
Yeah, you know, almost everywhere else in the world, they're actually increasing their harvest levels to be more at the sustainable management level. So you know, whether it's Germany or Sweden or I think it comes down to that there's still people that very much believe that all forests need to be protected. That's the best climate change solution we have. We need to stop harvesting and you know, preserve and protect our forests. And what you know, and I think that is actually how basic it is. I think there's just this a portion of society. It has more influences in different jurisdictions. I think here in British Columbia, it's a very strong conservation mandate. It gets a bit distorted because we have old growth forests, which have there's a different argument around old growth forests. There's good reasons why we would want to protect more of our old growth forests. But when you look at forests that go through natural disturbances, which is, you know, Scandinavia, arboreal forests here in Canada, the montane forests, even in the Kootenays throughout the United States, it's just misunderstood the role. And I think even the bucket 3 role is also incredible. Plan A is to manage sustainable working forests. If Plan B was to stop all harvesting, it would be a climate change disaster. If you think about having to replace all of those materials, single-use plastics, energy, steel and concrete, if that was your only solutions for society to build homes and to provide energy, that actually is an absolute disaster. And we're talking, you know, significant increase in orders of magnitude increase in emissions. So that's where that bucket 3 is not well understood by our stakeholders, and I think that is one of the key parts of what we have to do is get out there and help educate people with the science.
Yeah. Can I just add
Yeah, go ahead.
to that? Yeah, I'll also add the structural aspects that are quite different. In Canada, it's publicly owned. In a lot of these other places we're talking about, it's private ownership. Private woodlot owners, these owners have a different mentality. When you own something, you care for it, but at the same time, you recognize that it's an income generator, et cetera. Whereas what we have here is a history of government looking at this in the past, at least, as a cash cow that that served public policy concerns. And I think this underlines a lot of what our problem is. And this is why we were reflecting on, if we can see these streams come in of revenues that could be then used to move the forest management strategies to a way that will result in better forest management, and this will mitigate the fire and disease issues, I think, quite significantly. So I do think that these are at play, and that we really have to be looking more aggressively at this. There's very little incentive for governments today to actually carry this. And the other big thing is there's little incentive for companies to do that. That stewardship aspect often is looked at as doing the minimum. If there was incentives for those companies, and we did a project in Alberta in this regard, that they could be incentivized to maybe be able to harvest more if they were more diligent in terms of forest management, this would change the situation, I think.
And I think maybe the last point is, it's a natural resource, so any forest on Crown land is a provincial responsibility, so it varies from province to province.
Yeah.
And so there's no way of putting together a national approach to this.
So if I could just ask a follow-on. So a couple of weeks ago, I read an article, and I don't really follow the names, but you listed down like this Mercer and Resolute and the rest of it. But there's some Indonesian company that seems to have
Paper excellence, yeah.
bought everything.
Yeah.
So what's the impact of that? I mean, what's their obligation for sustainable forest management? Will they do it better because that's how they do it elsewhere, or will they do it worse because, it seemed that we just sold the entire Canadian forest product to Indonesia.
I'm glad you're saying it. And their track record in terms of things, at least from an Indonesian perspective before, has been problematic, so it'll be interesting.
Okay, so
I would say, definitely the, paper excellence and, obviously Resolute and Domtar are all under the same umbrella that can be linked back to the Indonesian ownership. I mean, I think that the nice thing about Canada is that we do have, our provincial regulations for forest management is very strict. And so the minimum requirements, are very high in terms of everything from social elements for Indigenous rights and to community involvement in forest licenses, provincial regulations, sustainable harvesting levels that get set by the province. So, no matter what country you're from, if you're going to run a pulp mill with forest operations or a sawmill forest operations in Canada, you're going to do it to a much higher minimum standard with high levels of regulation and enforcement than compared to many places in the world. So whether it's Indonesia or other areas that are just, even if they had the regulation, they may not even be, following them. So, I don't want to be too hard on paper excellence. And, the other thing is they're buying companies like Domtar and Resolute that have been incredibly responsible for many, many years. A lot of those leaders are still the same leaders in those companies. And so I think, just to automatically say, well, hey, the Indonesians aren't doing it well, I don't think really reflects how Paper Excellence Canada is intending to run their forests and from a sustainably managed
So I was
perspective.
almost wondering whether
Yeah.
this was whether they were going to take us more towards the European management practices, and what you're saying is that they're not going to
Yeah.
have any more luck doing that.
That's right, yeah.
Very informative presentations, but it's pretty much based on the forest and product, right? And but you also talk about the chemicals. That's actually is the one that engage extensively the technology. I think the current interest actually, to a great extent, on the biomass waste, and coming from the rice husks and coming from the sugar cane bagasse, and the corn cups, and I come from Ohio, and that's why people use that as the feedstocks to do so. So I think I'm interested to know how how would you suggest the way to do so, and then a lot of gasification technology is going on right now, and I think that the issue here has to do with the tar, and pyrolysis is one of the very typical methods to do so. Do you have any thoughts or suggest as to, if you deal with the bio waste and how you go about doing it? And there are a lot of technology at the research level and to move on.
Yeah, maybe I can take that one. Certainly a lot of the technologies that I've talked about can be used with, well, okay, lignin extraction from a pulp mill is a specific process that only works because trees have a lot of lignin in them. Sugarcane does not, neither do, corn does not, wheat does not. So the nature of the residues are different. Brazil burns their bagasse to make heat and power to drive their fermentation plants, their ethanol plants. There needs to be there's a fair size heat demand there. But there's leftovers, and the same thing with the agricultural residues. There are leftovers, and there's a whole range of things you can do with them. And yes, gasification and pyrolysis are among the pathways. To me, those are a bit of a big stick approach. Breaking it down to carbon monoxide and hydrogen, and then reassembling it is to me, it's the last approach if you can't find something simpler to do with them. But I don't know that much more about it. This is not something that the forest sector faces because our bark largely gets burned for heat and power and exports to the grid, as Bill has described.
Yeah, could I just add one quick point? With respect to ag residues, as was just mentioned, I guess you're referring also to DOE and the level of effort that they put on the agricultural side. I would say that if you look at the billion-ton challenge and you look at the data in there, you find the ag residue is the biggest piece of the pie. In Canada, the big piece is the forest residues, and I think that's one big reason.
Do we have other questions?
I do have one more. So the Academy sort of got involved in this project, which we're going to be doing some workshops around, extending the northern boundary of the boreal forest. So this has been led by Yuri Levenko from Waterloo and Richard Boudreau from the First Nations University, or in his role with First Nations University. So apparently what's happening is the boreal forest is moving forward by feet a year, and the temperatures that it should support boreal forest is moving forward by kilometers a year. And so the question is, how do we sort of goose the forest so it keeps up with the temperature? And so the research project is to go out and see what it takes to actually make these things keep up. And the simple idea is that if the northern border of the boreal forest kept up with the temperature profile, that in fact that would represent Canada's entire need for a greenhouse gas sink, because it's a huge strip straight across the country. On the other hand, if we're net a creator and the stuff keeps burning down, it's unclear that that math works. And we're also going to a series of indigenous communities and explaining to them why having forest around their communities is a good thing, while we're watching other ones be burnt to the ground because they're surrounded by trees. So there's something a little wrong with the picture, but the actual concept is compelling. So I just wondered if you had some thoughts about how, and then there's the whole issue of whether you need to plant mushrooms before you plant trees. So
Mycorrhizae.
there's actually anything in the ground for the trees to live on, and so on and so forth. But yeah, it's an interesting project. We're involved with it.
Well, there's a strong indigenous element to that too, which is kind of neat, is to get them engaged more in this type of thing. Presumably, they'll be a key player in this. But again, the issue is this all, what you're saying in terms of the numbers are right there. I mean, there are approaches of learning from experiences where the temperatures have been traditionally cold, warmer, I should say, and by south. And there is work being done where species that are adapted down there are being looked at to move north. But then you get into issues with provincial governments on invasive species of trying to bring that in and what have you. If our forests were more intensively managed, like in Europe, at least chunks of it, it doesn't have to be the whole aspect, we might be better off in terms of being able to really bite into these kinds of issues. But I don't think we are now, to the degree.
With, considering the state of the forests now, especially since the bugs got into it a number of years ago, how quickly would we be able to turn into a forest management situation that would even approach what you see in Europe?
Yeah, the reality is we are going to need to be very patient. You know, I remember, you know, flying from Vancouver to Prince George during the sort of peak epidemic of the mountain pine beetle, and it was actually incredibly depressing to see these red and brown forests for literally, you know, it's what, about an hour, a little over an hour flight, an hour and a half flight, but for, you know, the 500 kilometers, we lost 17 million hectares of mostly, you know, lodgepole pine forests. And, you know, so now, good thing is when you fly over that today, it's incredibly green. And most of the forests are, you know, either in recovery, and a lot of that was harvested and replanted. Some of it, there was so much of it, we couldn't get to all of it, so it died and is actually naturally regenerating. But you know, those particular regions are, you know, kind of probably, you know, 80, 90 year kind of traditional forest before they would go through another insect or fire regime, and that's changing. And back to your, you know, your earlier question, you know, one of the challenges we have is that climate change is really changing forestry, and we're learning on the fly here. And you know, the Canadian Forest Service is doing some great work on that. They've got some amazing climate scientists and being people to sort of recognize. But our forests are changing as we're trying to make these decisions around what is sustainably managed forest. So climate change is throwing a bit of a wrinkle into it, but nevertheless, we're seeing, you know, the pine forests are growing back. They'll be fantastic forests in 70, 80, 90 years. And you know, we're going to have a choice then. Do we allow them to become susceptible again, or do we actually manage them in a more intensive way? And that's a decision, you know, that's in the future.
Do they need to be managed during those 70 years?
Well, you know, that is one of the biggest differences in when you go to places like Finland, where you see, you know, thinning, and then that allows the trees that are remaining to grow more quickly, and those are generally more set aside for the sawmilling industry. You know, we're such a vast country. You know, when we build logging roads, we build them kind of for a single pass approach, and so you know, there is definitely a lot of work going in right now in British Columbia around adapting the forest management to more intensive, where we are going in and doing thinning. That's just starting, and to see if we can incentivize the companies to go in and do that. And those would often be used in the pulp industry, kind of lower quality, smaller logs, and also to some degree in the sawmilling sector. But you know, those are the kinds of changes we really need to think about to make sure that we get the full benefit of those mitigating benefits.
When would it be realistic to expect a net benefit where the forest actually starts to suck up more CO2 than it puts out right now? Right now, the balance is the wrong way. What's the time frame? If we really put our minds to this and the provincial governments came on line and everyone decided community-based involvement and so on, what's the time frame?
You know, I don't have a good answer for you. I know that that work is in progress and trying to understand, you know, how these forests that are way more susceptible, not only to forest fires, but massive forest fires that are very difficult to put out and that actually leave the forest in much worse. When a forest fire goes through a sort of traditional, you know, 70, 80-year-old forest, it burns in a certain way and the forest regenerates. When it's a 120-year-old forest with a lot of, you know, fallen timber and way more dense than it ever should be, the fires are way more intense. They actually destroy all organic material, and it's very hard to regenerate those forests. So that's kind of what we're discovering. So there's the science is emerging in terms of, you know, how do we address the forest? And of course, we're just going to have to also, so many of our forests are in remote areas, and there's been less active forest fire fighting in Ontario and Quebec, and their forests are actually in better shape because they actually allowed these forest fires to burn for the last 50 years. And in BC and Alberta, we've been much more aggressive at fighting forest fires, really successful at that, but it's completely distorted the age and generated this increased vulnerability.
Could I ask Bill a question, just very quickly on that? Yeah, because I wonder if we're looking at your experience in the piece, for instance, that you talked about. Clearly, companies in Canada, and you emphasized that a minute ago, have demonstrated, forest product companies, very strong corporate responsibility when it comes to taking seriously their responsibility in the forest. Isn't it time for maybe governments to start rejigging things and empowering licensees more to move forward faster? And a lot of these things that we've been talking about could probably be fast-tracked if the companies had a little more autonomy in terms of managing this. I mean, they have a record of doing it quite well if challenged.
And honestly, I think in Alberta, there is more sort of trust of decisions that are being made by forest companies saying, we think this is the best approach. It's always a collaborative approach, not just with government, but other stakeholders. I'll give you a great example in Germany. I mean, they call it beetle-killed wood here. It's called calamity wood there, and it's not just so it's actually the spruce beetle that's really damaging it. But literally, because the forests are private, if someone gives our forest management group a call, it's called Mercer Holtz, says, I think I've got spruce beetle in my forest. We're usually there 2, 3, 4 days, 5 days. We've got a plan, and we're harvesting that either that year, at the very latest the next year, because spruce beetle really has a quick impact on the quality of the lumber. That's that guy's retirement. And many of the forests are on their 7th or 8th rotation. We're talking to people whose that forest has been in their family for 400 years, and they're looking forward to giving it to their grandchildren to harvest. You know, that. So they respond. It's like we're in there harvesting in weeks, if not months. You know, at the worst case, a year later, because the forest owner, he's trying to recover his economic loss without that. That would take multiple years. One of the challenges we had, and one of the reasons we lost 17 million hectares in British Columbia was it started in a park. The government said we can't touch the parks, and honestly, the Canadian national parks are a climate change disaster. The amount of emissions coming from places like Banff and Jasper and like I don't even want to get into that. Canadian Forest Service actually was restricted from issuing the report because the federal government realized how this is not the way you have to manage forests. So you know, that's part of this paradigm that we have to make sure we help our stakeholders understand.
I think it's time to, I think our time is up, isn't it?
It is. I am just looking around. Do you know if the elder has arrived?
Behind you, Rob.
Oh.
All right.
So, yes.
So
Please.
I would like
let's
to thank the speakers. Thank you.